Hello everyone, welcome to my channel. My name is Mohit Sharma and in this video we will see what is the use of p-values and how it is useful in making decisions. So let's get started. So let us first talk about the problem. Okay. So in real life the data is never clean and there is always some noise and things go up and down even when nothing real is happening. Okay. So sometimes you look at a result and it looks really good. So the numbers also look strong and the graphs also look nice. But many times that result happened just by chance, okay, which could be dangerous. So because if we trust every result that looks good, we will believe a lot of wrong things. Okay. So we know that we have to stop and ask one simple question. Did that result happen because something real is going on, or did we just get lucky? So that question is the whole reason p-value exists. Okay. So the idea of a p-value actually starts there. So whenever we calculate a p-value, we don't start by saying that something strange is happening. Okay. So we actually start from the opposite side. We start by assuming that everything is normal. Okay. So this starting assumption is called the null hypothesis. So in simple words, we say that let's assume that the simple thing is true. Okay. So in this example, the simplest thing is that the coin is fair. That is our assumption. And if the coin is fair, then over many tosses, we expect roughly the same number of heads and tails, 50-50. Okay. So not exactly equal, but maybe close. So something like 50 heads and 50 tails. But in reality, when we toss the coin and we see 95 heads, so at this point, you don't need any math to feel that something is off. You will immediately say that this looks strange. Okay. And then the p-value is trying to answer one question here. If the coin really were fair, how unusual is it to see something like this? Okay. We are not saying the coin is cheating yet, but we are just checking how well this result fits with your original assumption that we have taken that the coin is fair. Okay. So now comes the logic of the p-value, and we already saw that something unusual could happen, like 95 heads out of 100 tosses. So now the question is, how shocked should we be if everything were actually normal? Okay. So a p-value simply asks that if my starting assumption is true, so how surprising is this result? Okay. So imagine that if the p-value is 0.05, so it means that this kind of result could happen about 5 times out of 100. Okay. So just 5% of chance, which is not impossible, but it is just uncommon. Okay. So now if we have a p-value which is 0.0001, now that is a different, and this means that this would happen only one time out of 10,000. Okay, by chance. So at this point most people will say that okay, this is way too rare to ignore. Okay. And I mean this lead to a very simple rule that we should remember, that smaller p-value gives you more surprising results, or you can say that the smaller the p-value gets, the harder is it to believe that this happened just randomly. So you can say that p-value tells you that does this look too strange to be just luck or not. So in order to make a decision out of the p-value, we have to draw a line. Okay, that okay, beyond this point I will take this result seriously. So that line we call the decision threshold. Okay, so most of the time we set it to a value of 0.05. Okay, now what this actually mean in real life? So it means that if the p value is less than 0.05, then this result is rare enough that we stop blaming luck. Okay, or we can say that this probably didn't happen randomly. Okay, but if the p value is greater than 0.05, then the result is not that rare. Okay, it could easily be a random noise. So we don't reject the idea of luck yet, we are just saying that we don't have enough evidence, so let us not jump into the conclusions. So one important thing to understand here is that this rule does not prove anything, whether it is true or false. It is just a decision. Okay, so it helps us to avoid fooling ourselves when data looks exciting but might just be randomness playing with us. So that's what decision threshold is doing. Now there is a common misunderstanding that a lot of people think that a p-value tells you the probability that something is true, which is actually wrong. For example, if you see a p-value of 0.01, so many people would immediately think that okay, so there is a 99% chance that the coin is cheating. Okay, so that's not what it means. A p-value is not telling you how likely the coin is biased. It is also not telling you the probability that your idea is correct. It is only answering the question that if I assume the coin is fair, how uncomfortable does the data make me feel? Okay, so a smaller p-value just means that data does not sit well with the assumption of fairness. Okay, but notice something important, that a p-value is judging the data, not the truth. So it measures disagreement between what we assumed and what we observed. Okay, so there is another trap that people fall into it all the time, that when people hear a small p value, they think that it is telling them that the truth of the situation. So if they see p equal to 0.01, they think that okay, there are 99% of the chance that the coin is cheating. So that sounds reasonable, but it's not what p value actually doing. A p value never tells you that the probability that something is true or false. Okay, so all it does that it just the assumption you started with. Okay, so you started by saying that let's assume the coin is fair. Now the p value asks, if I stick with that assumption, how awkward does this data look? Okay, if the data looks very awkward, the p value becomes too small. So a small p value is basically saying that if the coin were really fair, this result would be pretty hard to explain. Okay, that's it. So imagine you flip a coin 1 million times. Okay, and at the end you see 51% heads. Okay, so is that different from 50%? Technically yes, but because you have so much data, even this tiny difference looks very unlikely to be pure luck. So the p value becomes very small, 0 less than 0.0001. Okay, so which is extremely small. So statistically it's significant, but let's be honest, that is the coin really biased in any meaningful way? So what's going on here? The p value is saying that the result is unlikely to be random, but it is not saying that the result is very important. Okay, so again the p-value only talks about the chance and not about the size. So it tells you how unlikely this result is if nothing special is happening. So it doesn't mean that the small p-value implies the big impact. Okay, so let's take a real life example. Imagine there is a company that has made a new blood pressure medicine. Okay, so we can ask a simple question, that does this medicine actually work or not? So what will the researchers do? They will just don't they don't just give it to one or two people. Okay, they will run a proper experiment. So they take around 1,000 patients in total. So out of these, 500 people get the real medicine. Okay, the other 500 get a placebo. So placebo basically a sugar pill that does nothing. Okay, so one important point here is that the patients don't know who is getting what. Okay, so now before looking at any data, scientists start with a basic assumption that this is called a null hypothesis. Okay, and the assumption is very simple, that let's assume this drug does nothing. So in other words, if we see any difference in blood pressure between the two groups, we assume that it's just a random chance, not because of the drug. So this sounds negative, but it is actually a smart. Okay, so you first assume nothing special is happening, and then you ask, does the data force me to change my mind or not? So that is why we need a p-value. Okay, so after running the experiment, researchers look at the data and what they will observe. So people who got the real drug showed about a 10% drop in the blood pressure compared to the placebo group. Okay, but the key thing here is that it sounds promising is not enough. Okay, so they run a statistical test to check one question, that could this difference happened just by chance or not. So after doing the math, they get a p-value which is 0.01. So what it means? It means that if the drug truly had no effect at all, then seeing a blood pressure drop this this big, it will happen only about 1 out of 100 just by luck, which is pretty rare. So the researchers would say that okay, this is unlikely to be a random noise. Okay, so this is exactly how the p-value helps, that if the it says that if the drug did nothing, this result would be very surprising. Okay, so now comes the decision part, that we have already calculated the p-value and it comes out to be 0.01, which is clearly less than 0.05, which is usually the cutoff that people agree on. So because of that, we say that the result is statistically significant. Okay, so what it means is, it means that okay, this result is probably not just a random luck. So due to that, we will reject the null hypothesis, which is an idea that the drug does nothing. Okay, so just an important point here is that rejecting the null hypothesis does not mean the drug is perfect or it is a magic. It, it simply means that the drug is strong enough to say the drug likely has some, so the data is strong enough to say that the drug has some real effect. Okay, so that is how decisions are made generally. They are not just made with certainty, but with the evidence that makes pure luck very weak explanation. So let us also take a very common real world example. Imagine you are running an e-commerce website. Okay, so right now your buy now button is blue. Okay, so someone from your team says that okay, let's change it to green. So green looks more attractive, maybe your sales will go up. But before changing it for everyone, there is one simple question you need to answer, that will this color change actually increases your sale, or it is just a guess. So now you will frame a null hypothesis which will say that okay, the button color does not really matter. Okay, so you can also say that if sales go up or down on some days, that's just a normal randomness, but due to some traffic changes or maybe mood of the people, timing, all of these things. So blue or green, according to the null hypothesis, makes no real difference. Now the job of the A/B test or p-value is to check whether the green button actually beats blue, or whether any difference that we will see is just a random fluctuation. Okay, so in that experiment, what you actually do, you split your users into two equal groups. One group sees version A, which is the blue button. Okay, so about 10,000 users see that, and the other group see version B, which is a green button. So another 10,000 users see this one. Okay, so everything else on the website stays the same, prices, products, traffic, nothing is different. So now you will wait and you will collect your data. After some time you will check your results. Okay, and you notice something interesting, that the green button gets 200 more likes than the blue button. So many people would say that okay, green button works and we have to deploy it. But there is one question that one can ask: did green get more likes? Did green get more clicks? Is the difference real, or it is just by chance? So maybe today the users are in better mood, or maybe traffic quality is slightly different, or maybe it is just a noise. Okay, so before making a business decision, we need to first ask that the p-value, the same question that we always ask: if button color truly didn't matter at all, how likely is it to see a difference like this just by only luck? Okay, so we already saw that okay, the green button got 200 extra likes, but the what really matters is the p-value. Okay, so because the p-value will tell us how much we should trust this difference. So let us look into the two possible situations. So we have two scenarios, scenario A and scenario B. So in scenario A, we suppose that okay, we calculate the p-value and it comes out to be 0.25. So what does this mean? It means that a 200 click difference is actually quite common, okay, if button colors does not matter at all. So in other words, you can say that this much difference can easily happen just because of random daily variation. So it means that statistically this result is not significant. Okay, now look into the scenario B. This time the p-value comes out to be 0.001, which is very small. So it means that if button color truly had no effect, so seeing a 200 click difference would be extremely unlikely. Okay. So now this result is statistically significant. So the decision changes to that switch to green button. Okay. So that is a key lesson. The number of extra clicks is the same in both cases. So what changes is how confident we are that the difference is real. Okay. So let us summarize what we have studied so far. So at its core, the p-value is just a filter. Okay. So data is noisy, randomness can create patterns that look real. So the p-value asks one simple question: is this result surprising enough that we should take it seriously or not? Okay. So now remember the basic logic. We always start with null hypothesis. We assume nothing special is happening. The coin is fair, the drug does nothing, the button color does not matter. Then we look at the data and check the surprise. If the result looks too extreme to be explained by luck alone, the p-value becomes small. And as a rule of thumb, when p-value is less than 0.05, we pause and stay and say that okay, this deserves some attention. Okay. So, but most importantly, a low p-value does not tell you how big or important that effect is. It only tells you that the result is unlikely to be random. Okay. So you don't just look at the p-value, you also look at the effect size. Okay, when you do a good analysis. So how big that change actually is. So think of the p-value like a warning light. It does not give you the full story. It just tells you when noise stops being a good explanation. So I hope you like this video. Thanks for watching.